In this video, we're going to discuss combinations. So a combination is an arrangement of items that occurs when no item is used more than once, and number two, the order of arrangement does not make a difference. So the one difference between a permutation and a combination is this issue involving order. So when we talk about a permutation is going to be a collection of items where the order does matter. So in other words, if we were to take the same set of items and rearrange them, then we have a different permutation from the one we started with. Now when it comes to a combination, all we're interested in is the actual selection of items. So we have a larger set to choose from. We're choosing some subset of that set. And when we're talking about a combination, arranging the items in a particular order doesn't actually matter. So if we were to rearrange them, as long as we have the same collection of items, one combination is going to be the same as any other combination. So we're taking a subset of items, but the order we put the items in does not actually matter. So that's going to determine whether or not we have a combination or a permutation. So anytime we're doing a counting problem, one of the places to start is making the determination of whether or not we're looking at a situation that involves permutations or combinations. So let's start by just doing some practice with that. So for each of the following situations, all we want to do is determine, are we looking at a situation that involves permutations or are we looking at a situation that involves combinations? So here's the first setup. 6 students are running for SGA president, vice president, and treasurer. The student with the greatest number of votes becomes president. The student with the second highest number of votes becomes vice president, and the student with the third highest number of votes becomes treasurer. How many different outcomes are possible for these 3 positions? Okay, so technically speaking, we would be counting the number of ways we could have outcomes. But again, all we're interested in here is, does this situation involve counting using permutations or counting combinations? So the biggest factor here is the fact that we are assigning specific roles. So think of it as being an implied hierarchy. We're assigning the roles of president, vice president, and treasurer. So 6 students were running, so we're taking a subset of those 6 students to assign to these 3 roles. But if we were to take a subset and put them in any particular order, rearranging the order is going to make a difference. So say we chose maybe the first 3 in the set. If we were to list them in alphabetical order, we could assign the first person to president, the second to vice president, and the third to treasurer. If we were to take the same subset of students but put them in a different order, then different people are performing different roles. So in this situation, the order that we're putting the students' names in actually makes a difference. Rearranging the names is going to change the situation entirely. So that is our indication that this situation involves a permutation. So rearranging makes a difference, so this is going to be a permutation type problem. Okay, let's look at another one. 6 people are on the board of supervisors for your neighborhood park. A 3-person committee is needed to study the possibility of expanding the park. How many different committees could be formed from the 6 people? So notice, technically speaking, these problems are very, very similar. They have a different context, but we're still talking about starting with a group of 6, and then from that group of 6 choosing a smaller group of 3. The difference here, though, is as opposed to assigning the individual chosen people specific roles, in this case, we're just talking about choosing a 3-person committee. In other words, just a group of people. Think about it this way. If they were to sit at a table, it doesn't matter what order they sit in at the table. It's still the same committee. There's no specific person who sits at the head of the table. So because all we're doing is choosing a subset and there's no particular order implied, there's no, head of the committee, anything like that, that means that this particular situation involves a combination rather than a permutation. If we were to take any particular collection of 3 people from that original group of 6, rearranging the order that those people come in doesn't change the committee. The committee is still going to be the same set of people and order doesn't matter. So this is going to be a combination. Okay, let's look at another one. How many ways can you select 6 Blu-Rays from a collection of 200 Blu-Rays? Okay, this is also going to be a combination. Notice it doesn't say we're arranging the Blu-Rays, anything like that. We're not alphabetizing them. We're just choosing 6 out of the 200. So again, if we were to choose the 6 out of the 200, rearrange them, put them in any order, it's still the same collection of 6 Blu-Rays out of 200. So because there's no order involved in this situation, this is also going to be a combination. Okay, and then last, in a race in which there are 50 runners and no ties, in how many ways can the gold, silver, and bronze medals be awarded? So with this one, there's very clearly order involved. We're talking about a race. Who finishes first, who finishes second, who finishes third. Clearly there's an order involved in this situation. So we could choose one particular group of 3. If we were to arrange the order for those 3, then that means a different person gets the gold, silver, and the bronze from who would originally get them. So because there's an order involved in this situation would involve permutations. Okay, so we want to focus on combinations for now, but again, keep in mind, you have to make that determination of which type of counting situation you're looking at before you actually make any determinations about what type of formula or what to do on your calculator. We're going to use all of these in the context of probability once we get a little bit further on. So when we look at a probability problem and we're talking about counting, we're not originally going to be told, is this a permutation? Is this a combination type problem? We have to make that determination ourselves. So that's always going to be where we start when we're talking about doing a counting type problem. Okay, so we're going to assume that we're just looking at permutations for the time, or not permutations, excuse me, combinations for the time being. So if we're taking R items out of a total of n, in other words, taking R out of the total of n, R is the subset size, n is the collection we have to choose from, and we're taking combinations. In other words, we're just taking a subset from the larger group. We don't care about the order that we're putting these particular individual items in. We're looking at a combination. If that's the case, then the number of possible combinations is represented as NCR. So notice that's a very similar notation to what we looked at with permutations. We just have a C instead of a P. So in this case, NCR is going to be N factorial. So again, N is the number of items we have to choose from. It's the size of the larger group. So N factorial divided by N minus R factorial. So the size of the group minus the size of the subset, factorial, times R factorial. So notice this is very similar to the permutation formula. We've added on one factor in the denominator. That's the only difference. So having that one additional factor is going to adjust the number we have. In general, if we're talking about the same original sized set and the same size subset, there's always going to be more permutations than there are combinations because of that order issue. So rearranging the same subset gives us a new permutation, whereas it doesn't give us a new combination. So if we're looking at a similar problem, permutation versus combination, in general, the number of permutations is always going to be higher than the number of combinations. Okay. Now we talked about where we could find this button on the calculator. There are buttons to represent these kinds of problems in both the scientific calculator and in the graphing calculator. You are more than welcome to just use the combination button on the calculator, and of course I'll show you where that is. So let's look at some examples. Okay. So for each of the following, we want to calculate the number of combinations using the factorial formula. So I have it written out that way. And we're just going to do it in the calculator in order to demonstrate how this is going to work. Okay, so as with permutations, the biggest thing to pay attention to is the numbers. How many do we have to choose from? And then how many out of that group are we choosing? That's essentially the meat of the problem. Okay, so you volunteer to pet sit for a friend who has 7 different animals. How many different groups of pets are possible if you take 3 of the 7 pets? So we know this is a combination because there's no order involved here. We're not saying you're going to put them in the back of your car in cages in a particular order. You're just taking a selection of the animals to pet sit. So you have 7 to choose from. So 7 is going to be our value for N. And you're choosing 3 out of the 7. So 3 is going to be our value for R. So I have it set up using the factorial formula. So N factorial divided by N minus R, so 7 minus 3, which is going to give you 4 factorial, times, still in the denominator, R factorial, which would be 3 factorial. Now we're just going to do this on the calculator. So if you're using the scientific calculator, remember the permutation button is going to be under PRB, under there, so we hit that button and then we can find that. That's also going to be where the combination button is. So if you click PRB, Option 2 is NCR, so that's going to be our combination button. Now remember, in order to use this, we have to type the N first, then we go and choose this option, and then we type R. So let me clear back out and let me do that. So N is going to be 7. We're taking a combination, so PRB for probability. Scroll down to option 2, hit enter, so NCR, C for combination, and then R is 3. So 7 combination 3. And that's going to be 35 in total. So what does that mean? Well, that means there's 35 different ways that we can choose 3 out of the 7. Now, just for the sake of showing you how a combination differs from a permutation, suppose you were going to take 3 out of the 7 and you want to put them in your car in a specific order. So maybe one animal can't sit next to another animal and you want to determine how many different ways there are to rearrange them. So think of that as being kind of 2 parts. Combination is only 1 part. We're just choosing a subset out of the big group. With a permutation, we're choosing that subset out of the group and then we're arranging that subset as well. The arrangement part is why we end up with more possible, I don't want to say combinations, more possible permutations than we would if we're just taking about, or if just talking about taking a subset. So suppose there was an order implied in this situation. It would still be 7, it would still be 3, but if there's an order implied, it becomes a permutation problem. So let's pretend for a minute that it was a permutation problem. So N is still 7, we would go and we would choose P, and then R is 3. And that would take our total from 35 to 210. So in other words, if we were to take each of those 35 combinations and then look at all the different ways we could rearrange the subsets we've chosen, then there's going to be 210 ways to do something like that. So that just gives you a sense. If we have more to choose from and we're choosing more, you'll notice these numbers get a lot bigger, particularly those numbers of permutations. So it's kind of interesting to compare these just for the sake of seeing how different the numbers can be based on the situation we're in. Okay, let's look at another one. In poker, a person is dealt 5 cards from a standard 52 card deck. The order in which the 5 cards are received does not matter. What we want to know is how many different 5-card poker hands are possible. Okay, so notice in this situation it tells us the order does not matter, but keep in mind if you're dealt cards, you're just picking them up and you're holding them in your hand. If you rearrange the cards in your hand, it's still the same hand of cards. So because the order does not matter in this situation, we know this is going to be a combination problem. So we have 52 to choose from, 52 in our standard card deck. So N is going to be 52, and then we're dealing a hand of 5 cards. So that means R is going to be 5. So let me show you how you would do this in the graphing calculator, okay? So we found the permutation button under the math menu. That's also where we're going to find the combination button. So remember, depending on the type of graphing calculator you have, how old versus new it is, sometimes you have to type in first and then go find the button. Or depending on if you have a newer calculator, you may be able to just choose the option for combination and then type in an R. So with my particular model, you can do that. So if you go to the math menu, go over to the probability submenu, and then there's NPR, there's our permutation button. Right underneath it is NCR, so that's going to be our combination button. So I'm going to highlight that, I'm going to hit enter, and then again, notice it gives me the little boxes to type into. If yours doesn't give that, then that means you need to clear this out. You need to type your value for N first, and then you go back in and you find this, and then you type your R. Okay, so we have N equals 52, R equals 5, so 52 combination 5, big number, so 2,598,960. That's going to be how many different ways you can get 5 cards out of a 52 card deck, so a bunch of options. Now again, just to show you what this looks like versus a permutation, suppose the order they're dealt in matters. So in other words, maybe you can only pick up 1 at a time from a stack of 5, something like that. So having a different order actually makes a difference in terms of how you play the game. In that case, it would be a permutation. N would still be 52, R would still be 5, but it would be a permutation. Well, how many permutations would there be in a situation like that? Let's see. So I'm going to choose the permutation button. N is 52, R is 5. Look at the difference. That's a big difference. So we went from about 2.6 million to, count it, 3 places, 3 places. So that would be 311 million. Major difference if we're talking about order. We're only talking about combinations here, but if there was an implied order, again, notice the difference between the two. Major difference. Okay, I just wanted to show you that for the sake of seeing that. We'll just do the combination component from here on out, but just so you're aware, that's just something to keep in mind. Okay, another one. A book club offers a choice of 12 books per year from a list of 40. And how many ways can a member make selections for the year? Okay, so we're choosing from a list of 40. We're choosing 12. Now notice this does say per year, so ideally you would think if there's 12, maybe you go month to month to month. However, in this case, it doesn't say we're worried about which one we choose for January versus February versus any other month. We're not worried about the order we get them in. We just want to choose the set of 12 books that we're going to get for the year. So N is going to be 40. That's the number we have to choose from. And then R is going to be 12 because we're choosing 12 out of the 40. So let's see how many that's going to be. So N is 40. Go to the probability menu. This is a combination because there's no order involved. And then we're choosing 12 out of the 40. Look at that. Look at that number. That's insane. What is this? So there's 3 places. There's 3 places. So that takes us into the millions. 3 more places before we get to that last 5. So that's thousands, millions, billions. Literally, that is roughly 5.6 billion combinations, different ways to choose the 12 out of the 40. It's kind of hard to believe that that's the case, but if we were to go through and just try to make a list of all the possibilities, choosing 12 out of 40, eventually you'll find that you run out of steam and you just can't do it. There's no way we could actually enumerate all of those just in a reasonable way. So believe it or not, that's actually how many it comes out to. And again, if this were a permutation, imagine how much bigger that would get. Okay, let's look at a few more. Okay, so for each of the following examples, again, we want to calculate the number of combinations, but we're going to take it up a notch. Okay, so I want you to think back to the fundamental counting principle that we talked about before. So remember, the fundamental counting principle just says if you're performing a sequence of steps, if you want to calculate the number of ways that you can perform that sequence, you're going to multiply together the number of ways you do each individual step. Well, sometimes the individual steps are more than just, individual numbers that can easily be determined. Sometimes counting the number of ways to do each individual step is going to involve us using a permutation or using a combination or maybe some combination of the two. So you may have problems that combine these kinds of concepts together. So for instance, how many different committees can be formed from 5 professors and 15 students if the committee is to be made up of 2 professors and 10 students? Okay, now how do we know this is a multi-step process? Well, the reason we know this is multi-step is because we have specific requirements for what we're choosing. We want to choose professors, specific number, and we want to choose students, a specific number. Well, if we just lumped the 5 and the 15 together into a group of 20 and just chose the committee out of the 20, we don't have any guarantee that we're going to get the particular ratio we want for professors to students. So the only way to guarantee in a situation like this that we would get the numbers we want is to choose professors from professors and choose students from students separately. In other words, think of those like 2 steps in this process. We have to make each of those individual choices separately. So that automatically means fundamental counting principle. We're counting things in total, but in order to do this kind of problem with this particular setup, we have to perform a 2-step process. So step 1 is going to be choosing the professors. Now notice this involves just choosing a committee. So we're not talking about anyone's in charge, anyone is in a particular order. We're not worried about order, we're just worried about choosing the individuals out of the group. Okay, so for professors, we have 5 to choose from, and we want to choose 2 out of the 5. So it's a combination because the order doesn't matter. It's a committee. The order doesn't matter, so it's a combination. From the 5, we're choosing 2. So N is going to be 5, R is going to be 2. So 5 combination 2, which you can verify comes out to 10. So there's 10 different ways to choose 2 people out of a group of 5. Now the second step in the process is to choose the students. So we have 15 to choose from, and we're supposed to choose 10. So N is going to be 15. R is going to be 10. We're taking again a combination because the order doesn't matter here. 15 combination 10 is going to be 3003. Okay, so we've determined how many ways we can perform each step in the process. What we want to know now is in total. Put the committee together, put the professors, put the students together. How many ways are there to do that? Well, again, the fundamental counting principle says step 1, determine how many ways there is to do that. Step 2, determine how many ways there is to do that. Multiply those 2 values together. So multiply the number of ways you can perform each step in your process, and that's going to give you the total number of possibilities. So in this case, 10 options for professors, 3003 options for students. Multiply those together, and that's going to be 30,030. That's going to be the number of different possible committees we can get choosing from this group with this specific ratio in mind. Okay, let's look at another one. In January 2017, the U.S. Senate consisted of 46 Democrats, 52 Republicans, and 2 independents. How many distinct 5-person committees can be formed if each committee must have 2 Democrats and 3 Republicans? So in other words, we want to form another committee. We've got that specific ratio in mind. So just like with choosing professors and students, again, if we have that specific ratio that we want to meet, the only way we can make sure we're choosing and adhering to that requirement as well is to choose the Democrats only from the Democrats, and then choose the Republicans only from the Republicans. In other words, 2 steps. Choose the Democrats, step 1, choose the Republicans, step 2. Okay, so we want to have 2 Democrats in the group. We have 46 to choose from. Again, it's a committee. So it's a 5-person committee. The order doesn't matter. We're not talking about there being a specific chairperson for the committee. It's just a group of 5 people who plan to work together. So for our Democrats, 46 to choose from, combination 2. That comes out to 1,035. Now for the Republicans, we want to choose 3. We're taking this as a higher number, potentially because there's more in the Senate. So they're assuming that 2 choose 3, or 2 versus 3 is a little bit more accurately representative of the combination that's in the Senate. Okay, so 3 Republicans out of the 52. So 52 combination 3 comes out to 22,100. So we perform step 1. This is the number of ways to do that. We perform step 2. This is the number of ways to do that. We multiply the number of ways to perform each step together, and that's going to give us the total. So 1,035 times 22,100, 22,873,500. So that's the number of different committees we can form if we're choosing in this way. Okay, last one. A chemistry exam consists of 10 multiple choice questions and 5 open-ended problems in which all work must be shown. If an examinee must choose 8 of the multiple choice questions and 3 of the open-ended problems, in how many ways can the questions and problems be chosen? Okay, now notice, don't focus on the fact that it's multiple choice and you have a certain number of multiple choice options. Notice we don't know anything about how many multiple choice options there are. All we're doing is choosing a selection of problems to answer. So the professor has written a test that has a bunch of problems to choose from. You don't have to answer all of them. You only have to answer 8 out of the 10 multiple choice and 3 out of the 5 open-ended problems. So again, think of this as like a 2-step process. We're choosing multiple choice problems from multiple choice problems. We're choosing open-ended problems from open-ended problems. So for multiple choice, we have 10 to choose from, and we're required to choose 8. Now again, the order doesn't matter that we put this in. This is probably a numbered test, but it's just saying choose some subset of the problems and answer that subset. It doesn't say we have to answer them in a specific order. We're just choosing a subset of the total. So 10 combination 8 comes out to 45. And then from the 5 open-ended problems, we're choosing 3. So 5 combination 3 comes out to 10. Step 1, step 2, 45 ways to do the first step, 10 ways to do the second step. Multiply them together, and that's going to be 450 possibilities in total. So that gives you just a sense of what combination problems can look like. Anytime you see the word committee, unless you're talking about maybe the chairperson of a committee, something like that, that's usually a red flag that we're talking about a combination problem, because the order typically doesn't matter. When in doubt, just remember, fall back on that criterion. If there is an order implied in the situation, there's some type of hierarchy, or we're arranging something and the order, changing the order changes the situation, we know we're talking about a permutation. If we're talking about a situation where all we're doing is choosing a subset and there's no implied order, in other words, rearranging the subset doesn't actually change anything, then we know we're talking about a combination.